Alright, so what I do want to look at here is H, okay? This is a concept that initially may seem really simplistic, but there's a lot to this, okay? Talking about increasing and decreasing is really just part of the picture. So what I wanted to use today to do was to kind of build off of that and then tie it together with things that we learned quite a while ago. Because our goal is to be able to make accurate sketches and make some inferences about our functions. And then next week we're actually going to add another element to it when we look at the second derivative. So just try to pick up as much of this as you can now. Then when we add that extra element, it'll just be one more thing rather than trying to catch up and do that. So I want to look at H, and what we're trying to do is find and classify any stationary points, which remember are also known as critical values, okay, or critical points. Do it? Oh, there we go. Critical. Good. Okay, or points. Okay. Critical values which give us critical points. All right. So we're going to do that here, and then we're going to use those to sketch the function, and I will give you a little bit clearer directions, but showing all important features. Okay, you may say, well, that's very broad and very kind of open-ended. We'll talk about what the important features are here as we work through part H. Okay, but first of all, how do we find critical values? The roots of? Yeah, the roots of the derivative. It's when the derivative equals 0. So the first step in our process here is find the derivative, f prime of x, and what is that? Okay? And we've got to find where that equals 0. And here's where the stuff from a long time ago comes in. How do we solve that? Well, the first thing I would do is divide everything by 4. That gets my numbers a lot smaller. Okay? So if I divide everything by 4, I have x cubed minus 3x plus 2. If it were x squared minus 3x plus 2, this would be really easy. But we have a challenge here because we've got this x cubed minus 3x plus 2, and that doesn't factor real easily. So what could we do?
Wait, never
If it were an x squared, we could do that, but we can't do that in this case. Not a bad thought. We need a root, right? If we got a root, then we'd be able to use synthetic division, right, in order to factor that out. Okay?
Square root both sides?
Yeah, the P over Q thing, the rational root theorem. Do you remember that? Okay. That was like chapter 2 of SL1, so that was going on a year and a half ago almost. So it's been a while. Alright, so this is good that we're kind of bringing this up again, because you need to know how to do it. The rational root theorem says that the possible roots are going to be at x equals plus or minus any of the factors of the constant over the factors of the leading coefficient. We'll abbreviate that, okay? So in this case, the possible roots are plus or minus 1 or 2, because those are the factors of 2, over the factors of 1, which are just 1, of course. Okay? So we have 4 possible roots here. Positive or negative 1, or positive or negative 2. Everyone understand where we got those? Is it coming back to memory a little bit? Okay, by the end of the day you'll be able to whip these out, no problem. We'll do this in a bit. So now how do I test to see if any of these are rational roots? Okay, I can plug them in and just try it that way. Another way that will also get us what it factors into along the way is, you remember this? Synthetic division. So I have a 1x cubed, 0x squared, a minus 3x, and a plus 2. And then for our synthetic division, we add down, and then we multiply over. We multiply whatever we get down here by what we're testing. Okay, so 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, negative 3 plus 1 is negative 2, negative 2 times 1 is negative 2, and 2 minus 2 is 0. So what does that 0 tell us? That it's a root.
And we have the x squared now.
Very good. Yeah, now we know this could factor out of this x cubed minus 3x plus 2 as an x minus 1. And we know what's left over when we do that is x squared plus x minus 2. And now we have a quadratic that we can handle a lot easier.
Wait, how do we know that?
Because this was our x cubed column, and we're dividing by an x,
Right.
so it's going to end up being x squared,
Okay.
and so on.
And how do you know that it's x minus 1? Is it always going to be x minus that's in like the root?
Yes, it'll be the opposite of the root that you have. Think about what would make it 0. If I have a 1 in for x, I'd have to subtract 1 to make it 0. Okay? So now, that's equal to 0. This factors. Okay? So we have x minus 1 times x plus 2 times x minus 1. So now we know our critical values. Our critical values are at 1 and negative 2. 1 happens to be a double root, and we'll see what happens when that takes place. Okay? So now we can actually do our sign diagram, or our sign diagram. Okay? We put negative 2 and positive 1 on here. There's negative 2, here's positive 1. And remember, what that has now done is it's divided our entire graph up into 3 intervals. Okay? We have the interval going from, not a bracket, parenthesis, negative infinity to negative 2. We have that interval. We have the interval from negative 2 to 1. And then we have also the interval from 1 to positive infinity. And those intervals we're going to test to see if they are increasing or decreasing. Okay? How do we know?
You do the thing that we did yesterday. Wait. Or you see the arrows to see if they're mins and maxes.
Okay, we got to figure out the arrows in here, huh?
You can
Okay.
try -3, 0, and 2.
Yeah, we plug in a value. In this case, we could do -3. We could do 0 for that interval. We could do 2 for that interval. We're going to plug those into what?
Your original? No, the derivative.
The derivative. Okay, we're going to plug those into the derivative because we want to tell if it's increasing or decreasing. And we do that by seeing if our rate of change is positive or negative. Okay, is our derivative positive or negative? That'll tell us if we're increasing or decreasing. Alright, so if we do f prime of -3, that's going to be 4 times the -27, which is a -108, plus 36 plus 8. -108 plus 36 plus 8. Doesn't matter what it equals. We know that it is
Negative. Wait.
Yeah,
Yeah.
negative. Okay. So we know this is going to be less than 0. So our graph at this in this interval is going to be decreasing. Okay? So we'll put that with the decreasing. Okay? Does everyone see how we determine that? Alright, now we're plugging in 0 and f prime of 0. Yeah, that one's, you look at your thing, 0 gives us 8. So that's positive, which means we are increasing. Alright, so the entire interval from -2 to 1 is increasing. And now we can try 2. F prime of 2 equals 8 times 4 is 32 minus 24 is 16, or no, 8, sorry, plus 8 is a positive 16, so that's increasing again. Alright? If you wanted, you could say it's just increasing from -2 to infinity, or you can leave it like that. Okay? And really what we ought to do, since it's both of these, we would then say union. Okay? So, here's where the sketch comes in. Alright? I'm gonna do this. Okay? There we go. So there's all the stuff that we found so far, and I've got a graph here. We're gonna start graphing what we know. Alright? What points do we know so far?
Negative. 1 and negative 2.
Well, we know there are critical values at 1 and negative 2. We need the actual points, right? So we're going to plug 1 and negative 2 into the original function. Okay? So I need the point 1, and it's going to be 1 minus 6 is negative 5, plus 8 is 5, minus 3 is 0. Okay? So 1, 0 is right here. Okay? I'll just leave that there. And then I also have the point where x is negative 2. Negative 2 to the 4th is a positive 16. Negative 2 squared is 4, so we have a minus 6 times 4, it's minus 24. So 16 minus 24 is negative 8. Minus 16 more is a negative 24. Minus 3 is a negative 27. So we have negative 2, negative 27. So if I'm going to go by 2's on my y-axis, so here's negative 20, 22, 24, 26, 27. Oh, negative 2, negative 27 is going to be somewhere around there. Okay? Now, let's look at our sign diagram and tell what we know about these points. Okay? You'll notice here, to the left of negative 2, we're decreasing. That means we're coming down to negative 2. And then, to the right of negative 2, we're increasing. So we're going up from here. So what does that make this point, negative 2, negative 27? It's a min point, okay? It's a min point. And that's because we had this sign change from decreasing to increasing. Okay? Now, as we approach this point 1, 0, this other critical point, we're increasing up to it, but then we continue to increase after it. What do we call that point?
The axis of sin.
No. It's a critical point, but it's not a max or a min. It's a plateau point. Okay? We mentioned that yesterday. Okay? We mentioned that yesterday and in the flip video. We have a plateau point. These critical values, these critical points, will give us either max or min points, and those are the most common, or they can give us plateau points like this. Alright? Now, one other thing here, notice the minus 3 at the end. That means our y-intercept is at negative 3. So that'll help us sketch this a little bit better. Okay? Alright, this one's going up pretty sharply there. So now, the only other thing I need is, I see I'm going to hit the x-axis again over here. So I need to find that. Okay? I need to find my other 0. The nice thing with this, though, is the fact that this is a plateau point and it's on the x-axis tells us something about the 0 that's there.
Isn't that a 0?
It is a 0. How many roots does this equation have if we set it equal to 0?
4.
4, okay? Because it's x to the 4th minus 6x squared. When you had a 0 where it didn't go straight through, and it didn't come and touch it and then turn around, but it started to level off and then it went through, what was true about the roots there?
You have a multiplicity of 2.
Okay, we have a multiplicity. Here's a single root going straight through. If we had a multiplicity of 2, this is what we would see. It would come down, touch it, and then go back up. Okay? Now, a multiplicity of 4 would also come down, touch it, and go back up, but it would flatten out a little bit more. Alright? However, if we have an odd multiplicity, it's going to level off and then go through, like this one does here. So this, we could have a triple root or a quintuple root, okay, or a heptuple root, I guess you'd call it. What do I know it must be, though, in this case?
Quadruple.
Well, quadruple would touch and go back up. It's got to be odd.
But I thought that the original was to the 4th.
It is. Not all of them are right there, though.
Triple root.
It's a triple root, okay? Which means this function right here factors into x minus 1 cubed times something. Okay? Now, knowing that makes finding that 4th one really easy, because just like we did over here when we were guessing on roots and it happened to work out on our first try, here we already know it's going to be 1, so it's just a matter of reducing it down to figure out what it factored into. So if I work through that process using 1 with a 1x to the 4th, 0x cubed minus 6x squared plus 8x minus 3, we'll run through this pretty fast. You add down, multiply by the 1. So 1, that's 1, 1, negative 5, 3, 3,
You're low battery.
0. Oh, thanks. So now I know it's x minus 1 times x cubed plus x squared minus 5x plus 3. Alright? That was the first one. Let's take out another one. So 1, 1, 2, 2, negative 3, 0. Okay? So we're not going to, that was the remainder, so we're not using that in the second step. Okay? And this is the remainder, which is 0, which we knew would happen. So now we know we've taken out x minus 1 twice. The result is x squared plus 2x minus 3. However, I know that's going to factor into another x minus 1. And what's the other factor going to be there?
Plus 3.
X plus 3. So I know my last 0 is at negative 3. Alright, so as I come back up here, very, very slowly, there we go. I'll get rid of this, okay? I know I'm going to cross here at negative 3, okay? Draw for me. frozen? Not quite. Let's try this again. Is it gonna do it or not? Let's see. Oh,
Just 'cause they do
there we go.
Yeah.
Okay. So I need to go up a little steeper than I initially was drawing it, so I erase that down there. I come up here, hit that, and then continue on up. Alright? It's a little bowed out, but you guys get the idea. There we go. Okay? So. Alright, so here's our graph, goes all the way down here. There we go. Clean it up a little bit. Alright, so does that make sense? Pretty much? Okay. Now, there's a lot to these. I mean, that all was just one curve sketch. Okay? But we're then able to figure out a lot of stuff about this function. You know, we know where it's going to equal 0. We know where it's increasing and where it's decreasing. Okay? We're able to figure all that stuff out because we found all of these different points. Okay? So, anyone have any questions about what we have done here? Anything? Yes. All right. So this is our first main application of the derivative, is being able to do curve sketching and actually find intervals where we're increasing and decreasing and find these critical values. Okay? Now, what I want to look at today is looking at the sign diagram when there's more than just the critical values that we have to take into account. Alright, here we have a rational function. And what we find is that any points of discontinuity, whether it is a hole or whether it's an asymptote, those are points that we also need to consider as we develop our sign diagram. Okay? So if this is going to be my sign diagram, I need to find critical values, but I also need to find things that are limited from my domain, or excluded from my domain. So anytime you have a rational function, that's something that ought to stick out to you. In this case, what is x not allowed to equal?
3.
3 or?
Negative 3.
Yeah, 3 or negative 3. So, right off the bat here, I can put 3 and negative 3 on my sign diagram, and so I know I'm going to have at least 3 intervals here. Then I need to find my critical values. Okay? As we've already seen, we find critical values when the derivative is 0. How do we find the derivative here? Y'all should know this. How do we find the derivative here? Quotient rule. Okay? So, I know this whole thing will be over x squared minus 9 squared, because that's my v squared. Now I've got to do u prime v minus uv prime. Okay? So u prime, the derivative of my numerator, 3x squared plus 6x minus 4 times v, x squared minus 9, minus u times v prime. The v prime is a 2x. U is the whole numerator, x cubed plus 3x squared minus 4x minus 12. Okay? So now we have our derivative. Okay. We want to find where this does what?
Zero.
Equals 0. Alright, now if you've got a fraction and you want it to equal 0, does the denominator matter? No. Okay? Now, as long as the only thing the denominator matters for is the domain. Okay? Notice here though the domain is still a plus or minus 3 for the derivative as well. Okay? But let's go ahead and look at what would make our numerator equal 0. Now what am I going to have to do with that as I start to solve for where that equals 0? Come on guys. What are we going to have to do? If I want to get the numerator equal to 0, what do I have to do first?
Set it equal to 0.
Okay, set it equal to 0, and if I'm solving, distribute, okay? It gets a little messy, but you're going to have to distribute. So we multiply the 3x squared plus 6x minus 4 times the x squared minus 9. 3x to the 4th plus 6x squared minus 27, 6x cubed. I have a minus 27x squared minus 4x squared is a minus 31x squared. And then my x's are going to come from there, so that's a minus 54x plus 36. Okay, you all know how to distribute that, so. Alright, then we also need to distribute the negative 2x to that whole thing. So it's a minus 2x to the 4th minus 6x to the 3rd plus 8x squared plus 24x. So now we combine our like terms. We have 3x to the 4th minus 2x to the 4th, which is just x to the 4th. The 6x cubed minus 6x cubed is 0, so that's nice. We have a negative 31x squared plus 8x squared, so that's a minus 23x squared minus 30x plus 36. And now we have to figure out some roots. Alright, what are the possible roots?
3 negative.
Okay, 3 and negative 3, although those are outside the domain, they're possible for making our numerator 0. So we'll look at that because that'll at least help us factor as a possibility. How do we determine our possible roots?
P over Q.
Okay, and what does that mean?
The fact.
Constant over.
Factors the
coefficient.
constant over the factors of the leading coefficient. The leading coefficient's 1, thankfully. So that makes this a little easier.
1, 2,
Yeah, 1 and 36,
2,
2 and 18,
6,
3 and 12,
4,
4 and 9,
6.
6 and 6. Okay? So we actually have 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 possibilities. Okay? Now, for the sake of time, I'll tell you -3 works. Alright?
And you do synthetic.
You would do synthetic division. Alright? I usually just start with 1, then the -1, 2, -2, 3, -3. Okay? So,
Isn't there a rule with that where it's like if you plug in a certain number and you get like a negative or something like that, it can't be a number.
Yeah,
lower
it
than
cancels
that?
out a bunch of them.
I don't remember what the rule was.
you know, the first period was mentioned that as well. I haven't ever used that. I mean, I'm sure there is something, but I don't recall what that is, so.
I remember my entire paper was filled with numbers because I made one little mistake in the beginning and nothing was working out and it was driving me crazy.
Yeah, that'll,
Started,
Yeah,
it was,
yeah,
yeah.
a 75, 100, or
That was
0
really
or something.
one of the
Okay.
best things that brought me to tears.
well, hey, let's look at this one and get this one knocked out here. So we have 1x to the 4th, no x cubes, a -23, -30, and 36. Even though I know it works, I need to work it out so I know what it factors down to. Okay? So 1 times -3 is -3, -3 times -3 is +9, that's a -14, that's a +42, that's when I add down I get 12 times -3 is a -36, and I get 0. So that means this factors into an x plus 3 times x cubed minus 3x squared minus 14x plus 12.
Wait, this is
I have a
different.
question too that I can ask after class. I'm all ready. I'm done actually.
What are you? This is the domain. I mean, this is the whatever. The derivative. No, this is the derivative.
Is this, you just want me
You
to
said I didn't.
like I just want to list because I'm.
Yeah, that's fine. At least distribute the 3,
Okay.
but you don't need the FOIL.
And,
And that's true for all.
You guys finished the other day?
That, yeah, you can't do
You
anything
guys are
with
done?
that.
and,
Yeah.
So this is the active derivative.
Oh.
no, we
Yeah, if that's in the
I'm not
natural
going-
law, you can't take it out, so.
There's no way.
This is the same spec.
You're going one single.
This is
Oh, there's no way.
We don't know any
I'm gonna turn in my journal.
Here, like, only talks about, wait, when you're trying to
She likes my class sometimes. Yeah, we're 6th period. Isabella and
I just-
Well, that's where you have to apply other rules,
Like that, okay,
so.
I think so that this was finding.
All right.
This was-
Now, hey, one thing that will eliminate, if you'll listen here for a second, one thing that will eliminate some of the possibilities is now that it factored down and I have a 12 here, I know 18 and 36 won't work, and I also know that anything that's not a factor of 12, like 9, is not going to work. Now, at this point, I probably already tried 1 and -1 and 2 and -2 and +3. One thing, don't forget that you can have a double root. So what I would do is I would try -3 a second time, just to be sure. And because I know what the answer is. So, so we try -3 again. And we now have 1, -3, -14, and 12. Okay, so I bring down the 1, -3, -6, +18, 4, -12, and 0. Alright, so, okay, so I now know that x plus 3 factors out twice, And what's left here is an x squared minus 6x plus 4. We're down to a quadratic, which doesn't factor, but can be solved with the quadratic formula. Okay? Now, understand here that -3, while it is a root of our numerator, remember, it was out of the domain, so we wouldn't technically call it a critical value. All right, because it's outside the domain of both of our function and our derivative. Okay, so it's not a critical value. But our critical values we can find by solving this quadratic now. So positive 6 plus or minus the square root of 36 minus 4 times 1 times 4, so that's 16. All over 2 times 1. Okay? You guys know how to do the quadratic formula, so we'll kind of jump to the end. This ends up being 3 plus or minus root 5, which is 5.2 or 0.8, because the square root of 5 is 2.2. Okay? So now I have 2 more values to add to my sign diagram. Stop. There we go. Okay. I have 0.8 and I have 5.2. Okay. And this is where you could kind of help yourself out, because what do I have to do at this point? I know my critical values, I know where my domain excludes certain values. What do I have to do at this point?
Find the slope of the other points around him. and
Yeah.
numbers.
Yeah, I need to pick values in here like -4 and 0 and 1 and 4 and 6, and I've got to evaluate my derivative at those points, okay? Here's where you got to think. Use the work you've already done. I really don't want to plug all those into this mess right here. However, remember what that numerator factored down to. The numerator factored down to x plus 3 squared times x squared minus 6x plus 4, right? So, if I wrote my derivative as, that's fine, thanks, x plus 3 squared times x squared minus 6x plus 4 over my denominator, x squared minus 9 squared. Notice something here, because this makes this a whole lot easier. Whatever this is squared is going to be positive or negative. Or do we know? If I square something, it's going to be positive. And in my denominator, if I square something, it's going to be positive. So I really don't care what the values are. So now all I need to look at really is here when I'm trying to fill out my sign diagram. And that's a whole lot easier. Okay? So we plug these in. We can tell then what regions are increasing or decreasing. Then we can sketch this whole thing. Drawing in our asymptotes, using the critical values to find either max or min points, and of course using the general shape of the graph and all that too. Okay? These are complex. Practice some. Okay? Practice some. Alrighty, we'll let you go. Have a good day.
What is that?